Okay. All right, guys. So we are now in week 7. So how many of you are here? We have 45 students. Okay, we can start now. So guys, please make sure you have clicked your attendance. You clicked your attendance. I've updated all your attendance in Webble, in Web 2. Sorry, in Web 2. So you can check your attendance on there. And next week, Tuesday will be your test. Okay, next week Tuesday will be your test. So on this Friday, I'll brief you on all the test instruction so that you can be well prepared for next week test. Okay, on this coming Friday, we have 1 hour lecture class, right? So I'll brief you on all the test preparation. Essentially, there will be 2 questions. Okay, 2 questions, 2 hours. So 1 question is 1 hour. So you have ample of time. Okay. Public holiday, yeah, public holiday, but it's okay, right? We can have class, right? No issues with you, right? All of you are at home, right? Or do you want to have a leave? Because I don't see there's a need for, because we'll be having these classes in home base, so shouldn't be a problem, right, guys? Yeah. We can just carry on. Public holiday, every day we are at home. Yeah, tutorial, we'll be having tutorial as well. We'll be having tutorial after the class, which will be at 11:30 to 12:30. 10:30 will be your class, normal class. Okay. Okay, guys. All right. So I'll brief to you on all those test details on this coming Friday. Okay. Followed by normal tutorial lesson after that. Okay, now we are at week 7. So week 7 is lecture 7. So guys, rest assured, for today's topic, lecture 7, lecture 8, lecture 9, lecture 10, 11, 12, and 13, most of the contents will be on theory. So it'll be more of an information rather than calculation. Okay, so very interesting. Lecture 7 onwards, everything will be very interesting because lecture 1 to lecture 6, you have learned on the fundamentals, or I can say you have learned on the know-hows in atomic perspective. Okay, lecture 7 onwards, lecture 7, lecture 8, 9, 10, 11, 12, and 13, all those are on the application sides. This type of material is available, what kind of application that you can use it, and what properties does this material possess. Okay, you have metals, you have ceramics, you have plastic, processings of metals, manufacturing process of materials, and so on. All those are from lecture 7, everything will be on the application side. So things will be much more interesting, and let's go through then. So for lecture 7, I'm going to teach you on the types of ferrous and non-ferrous alloy. Okay, so guys, what is ferrous and non-ferrous at the first place alloys? You can write it down. Ferrous means an alloy that contains iron. Non-ferrous means an alloy that doesn't contain. I don't like to use doesn't contain, okay? It does contain iron, but in a very insignificant quantity. The quantity is insignificant, not significant. So some people say it doesn't contain, and so on. Okay? Wherever there is a content of iron, it does rust. Okay? Wherever there is less, when the quantity of iron is being reduced to insignificant scale, it means that there will be no rust. Okay, so that is on ferrous and non-ferrous alloys. So for ferrous alloys, it has a significant amount of iron. Non-ferrous alloy, it doesn't have a significant amount of iron. So the outline of this lecture today is I'm going to teach you on the types of carbon steel, what is stainless steel, and what is so big deal about cast iron, and also aluminum alloys. So aluminum alloys, aluminum alloys just less than 10 slides. I think it's over here. Let me see. Aluminum alloys. Okay, slide 26 to slide 31. So I'll cover these on this coming Friday and then followed by the announcement of your test. Okay, so today's lesson is until slide 25. So I'll be covering carbon steel, stainless steel, and also cast irons. So let's go in. Now we have metal alloys. Okay, the reason why we choose metal alloy to be included in your syllabus is because most of the engineering achievement, most of the engineering application deals with alloys, metals. Okay, deals with alloys, specifically metals. Okay. Further down the road from this subject, I'll be also teaching you on ceramics, plastics, and processing and so on. But let's focus on metal first. So metal classification, we have ferrous alloy and non-ferrous alloy. All right. So put aside non-ferrous alloy first. Let's concentrate on ferrous alloy. Okay. In ferrous alloy, we have steels and also cast iron. Okay, we have steels and also cast irons. In steels, we have low alloy and high alloy classification. Okay, in steels, we have low alloy and high alloy classification. Under low alloy, we have low carbon steel, medium carbon steel, and high carbon steel. Okay, and under high alloy, we have stainless steel, we have tool steel. Okay, cast iron classification, we have 1, 2, 3, 4, 5 types of cast iron. The first one is gray iron. Then we have nodular or ductile iron. And we have white iron, malleable iron, and also compacted graphite iron. Okay, so now we are in this ferrous. So let's talk about one by one classification of ferrous alloys. So low carbon steel over here, low carbon steel, medium carbon steel, high carbon steel. The difference between low carbon steel, medium carbon steel, and high carbon steel is the content of carbon. Okay, I'm repeating this, you can write it down. The content of carbon is distinguished by the parameters of low, medium, and high carbon steels. As you should, all of you guys should aware by now, the addition of carbon, okay, the addition of carbon into metal or iron leads to increase in ductility, increase in brittleness, and also the strength because of cementite, right? Those fundamentals are topic 6. So more carbon content gives you more strength. That's the reason why here we have tool steel. Remember your hammer should have a very high hardness value so that it can hit the nail and the nail can penetrate the any surface. So that's why we have tool steel here. Okay, so low carbon steel, the content of carbon is generally less than 0.25 weight percentage of carbon. Medium carbon steel, the carbon content is around the vicinity of 0.25 to 0.6 weight percentage of carbon. Whereas for high carbon steel, the carbon content is above 0.6 to 1.4 weight percentage of carbon. Okay, so these are the classification for low, medium, high carbon steel. So you might ask me, so what about carbon content of 1.4% and above? All those are categories as cast irons. Cast iron has very high carbon content. Okay. All right. Now, classification of plain carbon steels. Now you know that low carbon steel, medium carbon steel, high carbon steel, the variation is carbon content. And also prior to this topic, we have lecture 6 and lecture 5. I've teach you on addition of alloys, molybdenum, tungsten, nickel, chromium, addition of it. And also the carbon content varies a lot. Okay, you can go for 0.1% of carbon, 0.2, 0.025%, any percentage will do, as long as you are complying complying to the rules of where is it? Rules of this phase diagram for iron carbon system, where your maximum carbon content can only be until 6.70. So from this, you should be able to imagine that there are lots of classification of steels. So that is the reason why you need to have some the engineers, okay, material engineers need to come up with the standardization of classification of steel. Therefore, they have come up with the standard of steel that can classify steel according to the carbon content. So the classification always starts with 4-digit AISI or SAE code. AISI is American Industry for Steel Manufacturing something, okay? American Institute of Steel, all right? And SAE is Society of Automotive Engineering. Society of Automotive Engineering. So in 4-digit classification of steel, the first 2 digits indicates plain carbon steel. For example, 10 indicates plain carbon steel. So whenever you are what they call that looking for a steel, if the steel category starts from 10 something, it means that it is plain carbon steel. And remember, I told you something is the last 2 digit of the code. So the last 2 digit indicates the carbon content. Okay, please take note. The last 2 digit indicates the carbon content. All right. For example, 1030 steel. Okay, you go to hardware store, and then you ask, okay, I need this 1030 steel, and he'll give you the steel and having a barcode label 1030 AISI steel. So as a material engineer, you should know 10 stands for plain carbon and 30 stands for 0.3 weight percentage of carbon content in that steel. Okay. So as mentioned before, as the carbon content increases, steel becomes stronger and less ductile. It means that it becomes more brittle. All right. So highlight this. Carbon content, you should know these, okay. And then the classification, first 2 digit indicate plain carbon steel for 10 lah. Last 2 digit indicates the carbon content. Okay, and also guys, please don't forget that you should not have the thoughts that let's say carbon steel 1030, for example, carbon steel 1030 only have an ingredient of iron and carbon. No, that's not right. Okay, all alloys have an addition of another impurities, for example manganese. Okay, all plain carbon steel contains manganese. Having a values of 0.3 to 0.95 weight percentage to enhance the strength. They also contain other impurities, for example, sulfur, phosphor, silicon, and etc. Lots of content, lots of impurities as well. Right? So let's see. Okay, now applications of carbon steel. Very low carbon plain steel. Okay, very low carbon plain steel. You have a carbon content of less than 0.25. And of course, when the carbon content reduces, you reduces the strength. And if you reduces the strength, automatically it is much more higher ductility because you can slip along the plane. Okay, remember topic number 4, plastic deformation. All right. So it has a very low strength and high ductility. And it used, okay, the application for low carbon steel is used for sheet material for forming application. For example, car body panel or fenders. Okay, these are very low carbon plain steel. Okay, medium carbon content steel. Okay, 1020. So 2 weight percentage to 0.4 weight percentage. The application of those steels are used for shafts and gears, okay, which requires higher hardness. High carbon steel, very strong carbon steel, which has a content of 0.6 weight percentage to 0.95 weight percentage of carbon, used for springs, die blocks, cutter, or shear blades. Okay, most of these application, high carbon steel application, are used for tools, cutting tools, engineering tools, and so on. Roller mill, blocks, and so on. Okay. Now, what are the limitations? So now, the carbon steel have lots of application, right? But it has its limitation as well. So one of the limitations are it cannot be strengthened beyond 619 megapascal without losing its ductility and impact strength. So if you want to strengthen it beyond 690 megapascal, you need to sacrifice its ductility. That's the reason why we have annealing, we have heat treatment, we have tempering, and so on. Okay, and it is not deep hardenable. Okay, remember hardenable, the term. And it has a very low corrosion and oxidation resistance, very easy to corrode. And this plain carbon steel, rapid quenching leads to crack and distortion. Remember, rapid quenching from austenite to martensite, rapid quenching leads to crack and distortion because of thermal stress. It leads to crack, right? And also it has a very poor impact resistance at at low temperature. Okay, please highlight all these. You need to memorize these. So due to the limitation of this plain carbon steel, engineer tends to add more of these impurities. It's like cooking. You add more, let's see what's going to happen. So alloy steels may contain up to 50% of alloying elements such as manganese, nickel, chromium, molybdenum, and tungsten. So when you add more alloying agent into plain carbon steel, it becomes high alloy steel. Okay, so these are all high alloy steels. The first two digits is the principal alloying element or groups of elements in the steel, which contains the highest concentration. The last two digits, of course, leads to the content of carbon. Okay. So let's see one by one. It is not necessary for you to memorize these. It is just for your information, something like classification of steels. So 1,3 stands for manganese at 1.73 weight percentage. 40 stands for molybdenum at this percentage. And 41, if you go to hardware store and ask for 4120 steel, they'll give you stainless steel. This is stainless steel, chromium. Okay, all these are stainless steel. When the chromium content is higher, we call that as stainless steel. So 61, 52, 51, 51, 50, all those are stainless steel. 43 is nickel. 46, 47, 48 is all nickel. 44 is molybdenum, having a concentration of 0.53. And the list goes on. Okay, this list is not exhaustive. There's lots of list on it. Okay. And the distribution of alloying element. Okay, the distribution of alloying element depends upon the compound and carbide forming tendency of each element. So carbide is carbon, carbide is carbon, which is cementite. All right. So if you look at all the elements, these are the elements that can be added into carbon steel for you to create high alloy steel. For example, you have nickel, you have silicon, you have manganese, you have chromium, molybdenum, tungsten, vanadium, titanium, columbium, aluminium, copper, and lead. Okay, so when you add nickel into carbon steel, it will dissolve in ferrite, but it cannot combine in carbide. And this will be the compound, for example. Okay, when you add manganese in carbon steel, it can dissolve into ferrite, and also it can form a compound with carbon to form carbide. So these are the elemental element for carbide, and this is the compound examples. Same, the list goes on. Okay. All right. Now, let's talk about stainless steel. Stainless steel is being categorized as high alloy steel. Okay, if you look at slide number 2, it's over here. So stainless steel is categorized as high alloy steel. Okay. Stainless steel highly resistant to corrosion in a variety of environments. Highlight this. Okay, it is highly resistant to corrosion in a variety of environments, and usually stainless steel will be used as your kitchen cutlery. Okay, kitchen tools where most of your spoons, whatever things or tools that you have in kitchen is made of stainless steel, because you don't want to eat rust. Okay, I'm pretty sure that you don't want to have a rust element in your cutlery. Okay, so predominantly the alloying element is chromium. So in any plain carbon steel, when the chromium weight percentage is above 11%, we call that as stainless steel. Okay. Regardless of chromium, when you add nickel and molybdenum, it will also enhance the corrosion resistance. And this stainless steel can be divided into martensitic, ferritic, and also austenitic stainless steel. Remember guys, martensitic, ferritic, and austenitic is the what they call that properties of a material. What types of what they call the crystalline structure does it have? For example, ferritic is BCC, austenitic is FCC, martensitic is TCB. Okay. So ferritic stainless steel. Ferritic stainless steel is ferrum and chromium. Okay, iron and chromium binary alloy containing at least 12 to 30% of chromium, and it is in BCC phase. And the chromium extends alpha region, which is ferrite, and suppress the gamma region, forming the gamma loop, which is austenite over here, ferritic. Okay, it suppresses the gamma region, forming the gamma loop, which is austenite. Okay, and the properties of ferritic stainless steel is magnetic. And this material, ferritic stainless steel, is hardened and strengthened by cold work. It can be hardened and strengthened by cold working. You want to increase the mechanical properties in terms of tensile strength and yield strength, you can cold work it by reducing the surface area of the material. And ferritic stainless steel is low cost and used as a construction material with required heat and corrosion resistance. Any construction materials that requires heat and corrosion resistance, you can use this ferritic stainless steel. And the presence of carbide will reduce the corrosion resistance. Remember guys, higher the presence of carbide, it will exhibit corrosion. So more corrosion will exist. That is the reason why if you look at carbon steel, between low, medium and high carbon steel is more prone to corrosion because the content of carbon is higher. Okay. Now let's look at martensitic stainless steel. On martensitic stainless steel, it is under iron and ferrum alloy containing 12 to 17% of chromium and 0.15 to 1% of carbon. Whereas for ferritic is 12 to 30% of chromium. Okay, with very less or insignificant amount of carbide. But here we have some carbon content, which is 0.15 to 1% between this vicinity. And then for you to have martensitic stainless steel, what you need to do? You need to heat up let's say the carbon content is 17 over here, right? You need to heat up to a degree after the iterative temperature, and then you cool down rapidly, quench it so that it reduces the temperature, because these are not full what they call that iron chromium phase diagram. So you reduce the temperature to room temperature, so it will form martensitic stainless steel. So martensitic stainless steel form from quenching from austenitic region over here, austenitic region, liquid here, this phase or this phase. Okay, and it has a very poor corrosion resistance. Please highlight this. It has a very poor corrosion resistance. It is corrosion resistant, better than plain carbon steel. Just that when you're comparing with other stainless steel, for example, ferritic stainless steel or austenitic stainless steel, martensitic stainless steel has a very poor corrosion resistance, but it has a higher strength. Okay, and also martensitic stainless steel is heat treatable, and those heat treatment is used to increase the strength and toughness. Okay, same application for plain carbon steel. Okay, you can use heat treatment to increase the strength and toughness of the material, but for ferritic stainless steel you can't, because the carbon content is too low. You can also do it by cold working, where you purposely create plastic deformation. Remember cold working, guys? Try to recap back cold working. So martensitic stainless steel is tough and higher strength with a little bit sacrifice on the corrosion resistance. And this stainless steel can be used for machine parts, pumps, bearings. Okay, remember bearings, guys? Bearings all are corrosion resistant, right? And it must be very hard. So they are using martensitic stainless steel, and it tends to give out some corrosion, what they call that, properties after some time. Okay, and also valve parts. Okay, and martensitic stainless steel is also magnetic, right? Okay, now let's talk about austenitic stainless steel. Austenitic stainless steel is in FCC. Okay, and the chromium content is in the vicinity of 16 to 25 weight percentage, and you have nickel content as well, which is 7 to 20 percentage, and these are ternary alloys. Okay, martensitic is also ternary alloys, because not ternary alloy, it has only chromium content and also carbon content. For iron, for austenitic stainless steel, you have iron, you have chromium, and you have nickel, 7 to 20 percentage. Okay, so austenitic structure, which is FCC, austenite is FCC here. This remains austenitic at all temperature due to nickel. You have nickel, nickel is also in FCC. Austenitic stainless steel has a better corrosion resistance than other steel because the carbon content is much more lower. Okay, and it has a better corrosion resistance than other steels. And austenitic stainless steel used for chemical equipments, wear resistance, pressure vessels, and etc. And the alloying element for austenitic stainless steel can be columbium or niobium that prevents intergranular corrosion if the alloy is to use for welding. So remember, guys, nickel plays a huge role in corrosion resistance as well. It is being stated here. Nickel enhances the corrosion resistance. Okay. And austenitic stainless steel is non-magnetic. Whereas for martensitic stainless steel, it is magnetic. And for ferritic stainless steel, it is also magnetic. Okay, now let's look at the applications of stainless steel. So these are the AISI number 409, 446, 304, 316, 410, and 440. Okay, And then the condition is anil, all these are anil. This is Q and T is quenched and tempered. Martensitic, these are okay. Let's look at here, guys. Martensitic. Whenever you have martensitic stainless steel, all those are quenched and tempered. Whereas for austenite and ferrite, all those are annealed. Okay. And if you look at the tensile strength, ferritic is low, austenite is medium, martensitic is high. Okay. The typical application for ferritic stainless steel, automotive exhaust components, tanks for agricultural spray, okay, your aerosol spray, and valve, high temperature glass mold combustion chamber. For austenitic is chemical and food processing equipment, cryogenic vessel, and welding construction. And for martensitic is more of a robust and toughened material. So they use this in rifle barrel, cutlery, see cutlery, your kitchenware, jet engine parts, bearing, surgical tools. Okay, it's quite interesting to see austenite. They are using this in food processing equipment and cryogenic vessel. Does anyone can guess why? Why cryogenic vessel? Why temperature sensitive material? Does anyone can guess why here, guys? Let's see. Anyone? Anyone can guess why? Why austenitic stainless steel, especially for this formulation, they use in temperature sensitive equipments, chemical, food processing, or cryogenic vessels, or in a main role. For example, austenitic. Anyone can guess why, guys? High corrosion resistance. Yes, very high corrosion resistance. But what about temperature sensitive equipments? Okay, austenitic used for chemical equipments, pressure vessels. But it catches my attention. Cryogenic vessel. Why cryogenic vessel? There is very special properties for austenitic stainless steel. Anyone can guess? Heat transfer is low. Okay. All right. Okay. All right. Can you see the ductility? The ductility and strength is almost identical to martensite. But you look at the ductility is very high. So whenever you have ductility, and if you have a crack propagation, you have a very high strength material, at the same time you possess a very good ductility, it means that whenever there is a crack happening due to thermal stress, you can detect it prior. And also you can absorb the crack propagation because it is good in ductility, at the same time it is good in strength as well. So it won't blast, it will crack only. Okay, something very new for me as well, because I have no idea. When I saw this, it catches my attention, cryogenic vessel, then I look at ductility. Oh, okay, it's 40. Can you see, guys? It's very high. The strength is almost same as martensite, but the ductility is double from martensite. 5.5. This is 5.5, which is much more higher. Okay, interesting, huh? So, guys, your assignment, I will. This is the one that you need to do. Okay, you need to research on this. Okay, I will give you the assignment next week. Based on a, and you need to do research on the material to come up with why does this material qualify for your application. Lagging? Is it lagging, guys? Is it lagging? Can you hear me clearly? Okay, hold on. I've killed all the application, but still lagging. Is it okay now? Okay. Maybe Microsoft Teams are being sensitive to the word assignment. We try to filter out. Yeah. Okay. All right. Okay, so assignment, about assignment, guys, about assignment. Um, you need to pick up a material. I'll give you the assignment title next week. So essentially, this is where you need to master on. Okay, you need to look at the ductility, yield strength, tensile strength, and come up with the material properties. And you need to start writing the assignments on your understanding of the material from the application that you have chosen. Okay. So it's very interesting. Okay, very interesting. 40. The strength is high, which is comparable to martensite steel, but it retains the ductility as well. So temperature sensitive application, you can use austenitic stainless steel. Okay. Okay. So guys, just a quick recap. Stainless steel, we have three types. What is martensitic? Another one is ferritic, and the next one is austenitic. These are the properties of ferritic, martensitic, and also austenitic. And if you reduce the alloy in your plain steel, we call that as carbon steels. In carbon steel, we have three types, which is low carbon steel, medium carbon steel, and high carbon steel. And remember, as a rule of thumb, higher the carbon content increases the strength, reduces the ductility, increases the brittleness. Okay, so low carbon, medium carbon, high carbon. Low carbon 0.25 and below. Medium carbon you have 0.25 to 0.6. High carbon steel you have 0.6 to 1.4. Okay. Alloy steel may contain up to 50% alloying elements such as manganese, nickel, chromium, and molybdenum and tungsten. And also, guys, if you look at the classification here, you have plain low carbon steel and high strength low alloy steel. High strength means it might be martensitic or quenched heat treated steel. Same goes to here, plain and heat treatable. And here we have also plain and also tool steels. High alloy steel having an alloying element content which has higher than, where is it? 50%. Yeah. Okay. So this classification is under here. All right, guys. Any questions so far? Simple, right? Topic 7 onwards, everything is very simple. Is it simple or is it difficult for you to digest? Any questions, guys? Any questions? Is the carbon content always less than 1%? For which one? Qua Wenzeng. Which one are you referring to? Carbon content for which alloy? Is it low, medium carbon or high? Any alloy. Okay. For low alloy, the carbon content is being classified here up to 1.4. Above 1.4, if you look at the iron carbon diagram, above 1.4, somewhere around here, okay, you have another classification of steel, okay, but above 2.1 over here, all right, carbon content of 2.14 or 3%, 4%, 5% or 6%, 6 weight percentage, we call that as cast irons, which I'll be covering in a while. Carbon content is much more higher. Okay. When Hun. Higher carbon content is over here, lower carbon content is here, and the carbon content classification is until here. High carbon steel is up to 1.4, not less than 1. Right? Theo Tianzan, need time to digest. So maybe I can help you on that. So if you look at the skeleton of this topic, all steel is made of iron, right? So you have iron and non-iron. Okay. Now let's focus on iron. In iron, we have steels and cast iron. Steel classification has a carbon content of around this vicinity 0.25 to 1.4. Higher carbon content, we call that as cast iron. And under steel classification, we have low alloy, which has an alloying element very less. We are talking about 1%, 2% of alloying element. If let's say in all this alloy steel, in steel, we add more alloys regardless of carbon content, we call that as high alloy. And how much is the more alloy? It is 50% and above. That's all. As simple as that. So carbon content remains the same. 0.25, medium carbon 0.25 to 0.6, high carbon 0.6 to 1.4. Anything higher than this, we call that as cast irons. Okay, it's as simple as that. Very straightforward. Any other questions, guys, before I continue? Any other questions? Ferritic, martensitic, and austenites falls under low alloy subtopic. Nope, wrong. Lower Wenzhang, ferritic, martensitic, and austenite. Are you referring to slide number? Are you referring to slide number 11 or slide number 10? Lower Wenzhang. Okay, no, wrong. Okay, ferritic, martensitic, and austenite stainless steel. We are talking about stainless steel. These are under high carbon content, high alloys. Over here, stainless steel. It's over here. Okay, in general, it is under high carbon content. All right. So all these are what they call that high alloy steel. All right. Okay. So you can look at the composition here. 0.08% of carbon, 11% of chromium, 1% of manganese, 0.58% of nickel, 0.75% of titanium for this number. Okay. All right. Any other questions, guys? Okay, since there's no question, okay, we are good to go. Let's carry on. So now let's talk about cast iron, guys. Cast iron, right? So now I'm about to teach you on cast irons. So cast irons are over here. It's too much of diagrams. Let me clear these. Okay, now we are under metal alloys, ferrous, and cast iron over here. So cast iron, the keyword here is, please write down, the keyword here is a ferrous alloy with carbon content above 2.14. See, very high carbon content. So above 2.14 is the maximum solubility in austenite at the eutectic temperature over here, 2.14. That is the maximum solubility of austenite region at eutectic temperature at 1147. Okay, eutectic temperature. So practically, in general, practically, most cast iron contains between 3 to 4.5 weight percentage of carbon and between 1 to 3 weight percentage of silicon. Okay, not necessary for you to highlight this, but you just get to know on this. Practically, most cast iron contains carbon in between 3 to 4.5 weight percentage and 1 to 3 weight percentage of silicon. Okay, remember guys, the higher the carbon content, the lower the melting temperature. I've stated this on the previous lecture. Okay, the higher the carbon content, lower the melting temperature. So higher the carbon content makes cast iron easily melted. Since the melting temperatures between 1150 and 1300 are lower for those steels. If you look at here, this is the melting temperature over here. Look guys, the melting temperature is 1147. If the carbon content is being reduced, you can see 1200, 1400 and so on. See? So this is the mother of all slide. You need to refer to phase diagram. Okay. So of course, when you add more carbon, it is very brittle and it is amendable to casting. That's the reason why we call that as cast iron. Cast iron are easily casted. All right. For casting, there will be a brand new topic which I'll be discussing in the weeks to come on the processing of metals. Okay, we have few types of casting: investment casting, sand casting, lots of types of casting. So whenever there is a word casting of metal, you need to use cast irons. Okay. Another reason why cast irons are good for casting is because it is very fluid and has a very low shrinkage. It doesn't shrink much. And also it is easily machinable. And cast iron has a very wide range of strength and hardness. Okay, for example, you have gray cast irons, you have ductile, you have white, and also you have malleable. So all those are having very different, very distinguished, what they call that, strength and hardness. Okay, highlight these. And cast iron has a very low impact resistance and ductility. And the most common cast iron types are gray, nodular or ductile, white cast iron, and also malleable cast iron. Highlight these. Highlight these. Now let's go to one by one. So graphite formation and cast iron. Okay, now this is the phase diagram for cast irons, the formation of carbon. So most of the cast irons are in the mixture of alpha, which is ferrite, and also austenite. Okay, alpha and also austenite. And they have a mixture of graphite into it. Graphite is essentially carbon. Okay, in different what they call crystal structure. That's the reason why we call that as graphite. Okay. Now let's talk about gray cast irons. Gray cast iron, if you look into the microscopic view on gray cast iron, the graphite, okay, these are the graphites. Graphites are carbon. You can write it down. Graphite is carbon. The graphite exists in the form of flakes, the black color flakes, which are normally surrounded by an alpha ferrite, okay, which is BCC or pearlite matrix. So cast iron is essentially a pearlite having graphite. Okay. The carbon content and silicon contents are between 2.5 to 4 weight percentage of carbon or 1 to 3 weight percentage of silicon. So that is gray cast iron. And gray cast irons are very good in damping vibrational energy. So usually gray cast iron are used in structural material at the base of a building or construction base, because gray cast iron, one of their main properties is they can damp vibrational energy. Look at the vibration amplitude. Steel, it keeps on vibrating. For gray cast iron, no, it doesn't, because it is more brittle. Okay, higher carbon content. But gray cast iron are comparatively weak and brittle in tension. Okay, see, it's more brittle. It is brittle in tension. But if you compress it, the strength and ductility is much more higher. Okay, something like tar, tar roads. Okay, let's say if you slice a road, okay, let's say you have equipment to cut the surface of tarmac, which is road, essentially a road, into a dumbbell shape, and you are doing some mechanical testing on it. You try to elongate it. You can't elongate road, right? Because it is brittle. Can you imagine, guys? Can you do tensile test for road? It will crack because it exhibits brittleness. But when you compress the dumbbell shape of rod, you can't, because the strength is highest when it is in compressive state. Same goes to grey cast iron. For grey cast iron, when you compress grey cast iron, the strength increases, is much more higher, and also the ductility is much more higher. All right. So the sharp and pointed tips of graphite flakes serve as a stress concentration points when a tensile stress is being applied. So that's the reason why it is being weak and brittle in tension. So all these are sharp. All these are sharp points, and these sharp points acts as a stress concentration points whenever there is a tensile strength is being applied. Therefore, cracks happen at this point, and it just shatters whenever it is being pulled apart. Different story when you compress it. Okay. Strength and ductility are much higher under compressive loads. Properties. Grey cast used in the construction of base structure for machines and heavy equipment, since they are very effective in damping vibrational energy. And also grey cast iron exhibit a high resistance to wear. Okay, the wear resistance is higher, and it has a very high fluidity at casting, so that it can cast complex shapes in the molten state, and also low casting shrinkage. And grey cast iron is among the least expensive of all metallic materials. Okay. And under grey cast iron, you can also further modify the content by lowering the silicon content or increasing the cooling rate. Prevents the complete dislocation of cementite to form graphite. Remember, cementite is carbon content. All right. So lowering the silicon content or increasing the cooling rate prevent the complete dislocation of cementite to form graphite, and this will produce the microstructure consists of graphite flakes embedded in the pearlite matrix. Okay, more graphite flakes embedded in the pearlite flakes by lowering the silicon content or increasing the cooling rate. Next, let's look at ductile or nodular cast iron. So another classification or another types of cast iron is ductile, or we call that as nodular cast iron. If you look at the microstructure, graphite forms as nodulars. Okay, nodules or sphere-like particles. These are graphites. Okay, whereas if you look at grey cast iron, these are graphites. More of a flakes or rods. Okay, nodular cast iron is more of a nodules or spheres. So ductile cast iron is being produced by adding a small amount of magnesium. Okay, different ingredients, small amount of magnesium and or cerium to grey iron before casting. So essentially, this is grey cast iron. When you add more magnesium, okay, adding a small amount of magnesium or cerium before casting, you are creating ductile iron. That's all. Ductile cast iron. And of course, the matrix phase surrounding the particles are normally pearlite for an S cast piece. Okay. A heat treatment of several hours at about 700 degrees Celsius will yield a ferrite matrix. Okay, will yield a 700 degrees Celsius, will yield a ferrite matrix. Over here, 700 just below here, ferrite matrix. Castings are stronger and much more ductile than gray iron. Okay, these castings are stronger, very high strength, and it is more ductile than gray cast iron. And ductile cast iron retains the ductility, having high strength as well. Therefore, it has the mechanical characteristic approaching to those of steel. Okay, for example, ferrite ductile irons have a tensile strength ranging between 380 to 480 megapascal and a ductility of 10 to 20% of elongation. Most of the low alloy steel having high strength, for example, high carbon steel or medium carbon steel, it has high strength but at the expense of ductility. But for modular cast iron, it has the strength of steel but having a ductility of having a very high ductility, right? And since they have this kind of properties, the application for nodular cast iron, you can use that on valve because it needs a high strength material, pump bodies, crankshaft as if in your internal combustion engine, gears. Okay, gears can be also made by ductile cast iron, automotive and machine components. All right. Next, let's look into white cast iron. So the classification for white cast iron, it has a very low silicon containing less than 1%, whereas for gray cast iron, it has 1 to 3 weight % of silicon. White cast iron containing less than 1% of silicon. Most of the carbon exists as cementite. Okay, most of the carbon exists at cementite, not graphite, due to rapid cooling rates. And these cementite regions are surrounded by pearlites. So all these are cementite. All these are cementite and being surrounded by pearlite. These are pearlites. Okay. And gray iron forms interior region which cool more slowly. Usually white cast iron forms on the surface of the cast where there is a huge temperature gradient, all right, because of rapid cooling rates. So if you look into white cast iron, the formation of gray irons happen in the interior region which cool more slowly. And these types of white cast irons are extremely hard and brittle due to large amount of cementite phase. Okay, due to large amount of cementite phase. And these white cast irons are virtually unmachinable because it is very hard and very high wear resistance. And white cast irons are limited to application that is necessitate a very hard and wear resistant surface without a high degree of ductility. Okay, it has a very low degree of ductility. For example, you can use white cast iron as a roller in rolling mills. Remember rolling mills, the video that I've shared to you last time, where it shrinks or hot work material from bigger diameter to smaller diameter. So they can use white cast iron as the roller in the rolling mills. And generally, it is used as an intermediary in the productions of malleable iron. Okay. So let's talk about malleable cast iron. Now, malleable cast iron, graphites in the form of clusters. These are graphites in the form of clusters, which is very similar to nodular. It's surrounded by ferrite or pearlite matrix. Okay. So malleable cast iron formed by decomposition of the cementite as a result of heating white iron at a temperature between 800 to 900 degree for a prolonged time period. Having said that, heat treatment of white cast iron gives you malleable cast iron. That's all. Okay, when you heat treat a white cast iron, it will give you malleable cast iron because you are decomposing cementite and you are forming graphites in the form of clusters or rosettes. And these types of cast iron possess a very high strength with appreciable ductility. Remember guys, white cast iron, zero ductility, very brittle. Alright, not to say zero, okay, very high ductility, very low ductility, very high brittleness. Whereas malleable cast iron, we have some ductility because you already heat treated it and you are decomposed and you have decomposed cementite back into graphite over here. So this is very similar to nodular iron. Okay, remember nodular cast iron. And the application for malleable cast irons are connecting rods of IC engine, transmission gears, pipe fittings, valve parts for railroad, and also marine applications. Okay, so let's look at the overall system for cast irons. Okay, we have gray iron, you have ductile iron, you have malleable iron. All right. So gray iron, the material structure is ferrite pearlite, and pearlite. And these are the compositions of silicon. Look at gray iron, the silicon content is higher. Ductile iron, lower. Okay. Malleable iron, the lowest. And if you look at the ductility for malleable iron is almost as same as ductile iron. Okay. And these are the applications for each formulation of gray iron over here, and for ductile iron, and also for malleable iron. Malleable iron, the keywords are elevated temperatures, because at elevated temperatures you need to have some ductility so that crack exists as a crack. It doesn't fail the part, so you have some ductility. Okay. Any questions, guys? So all topic 7 is all on the application part, the understanding of the material. Any questions? Isn't that rapid cooling rate inhibit the formation of cementite? That is for, okay, if you look at rapid cooling rate, if you look at here, that is for plain carbon steel. We are talking about plain carbon steel having a carbon content of very low over here. Okay, but now you have a carbon content in the vicinity of this range. So the carbon content anyhow surpasses the energy level for iron. So that is the reason why whenever you have rapid cooling, it exhibits the formation of cementite over here. They're formed by decomposition of cementite as a result of heating white cast iron at temperature between 800 and 900 degrees Celsius. Okay, but if you look at lecture 5 over here, martensite. Okay, martensite prevents carbon diffusion. Okay, that's the reason why the carbon is being over here. Rapid cooling, the carbon doesn't comes out from the what they call that these cells to form carbide. Okay, over here the carbon content is higher, therefore the solubility of malleable cast iron is higher. If you look at here, guys, here we go. Look at the solubility of carbon in austenitic region is higher. So before this, we were talking about in a solubility range of eutectoid phase, which is 0.17. But now the solubility of iron have been increased to 2.14. Okay. All right, guys. Chinwai, look, can you understand? All right. Okay, let me show you another one. Two point one. Okay, no, not this. Okay, guys. Any other questions, guys? Any other questions? Any other questions from your side? Hello. Okay. Okay, guys. So you just need to go through this lesson again to make sure that you know the each classification of steel. Okay. Summary for today's lesson. Okay, you need to know what is ferrous metal, what is steel, what is cast iron, and the classification for each steel and cast iron. And for steel, you have low alloy and high alloy. What is the difference between low alloy and high alloy? What is the percentage? And under low alloy, predominantly it is under carbon steel. We have low carbon steel, medium carbon steel, high carbon steel. And high alloy, your alloying element content is above 50%. And I've gone through stainless steel. Okay. And also, regardless of alloying element, under steel, ferrous under steel, the carbon content is just up to 1.4%. Okay, above that, above 2.17 to be specific, we call that as cast irons. It is still ferrous metal. It is still ferrous metal, ferrous alloy. Don't get confused. Cast iron is still under ferrous material, but just that the carbon content is more than 2.1. Where is it? 2.14. So we call that as carbon. We call that as cast iron. The reason why we call that as cast iron, because it is easy to process using casting technique. Why it is easy to use as a casting technique is because here we go over here. It has a very fluid, low shrinkage and easily machinable. The main reason is because it is very fluid and also low shrinkage, where you can create complex shapes of the material. Okay. Any other questions, guys? Any other questions from your side? Nur Harpinder, you have any question? Okay, so all of you are okay, huh? All right, so next week I'll be continuing with aluminum alloys. Okay, and aluminum alloys. Aluminum alloys falls under high alloy steel. And then I mean not next week, this coming Friday. And then after that, I'll be discussing with you on the instructions for your test. All right. So I think if there's no question, that's all for today. That's all for today. If you have question, please ask me, or else thank you very much, guys. Just want to confirm midterm covers chapter 1 to chapter 6. Yes, midterm covers chapter 1 to chapter 6 up to last week. All right, guys. So that's about it. Thank you very much for your for your time. And if you have question, you can always type the question on the chat box. Okay. I see the face diagram. I sense fear. Face diagram. Actually, you can come up. You can join my tutorial class on this Friday if you wanted to join as well. I'll teach on the face diagram tutorial face diagram. It's easy actually. You just need to understand because lots of information is being poured on the face diagram. So a bit complicated, but once you have mastered it, it is easy because you're going to repeat the same step again and again. Okay. Okay. Compacted graphite iron. Compacted graphite iron is very similar to ductile iron actually. Very similar to ductile iron. Which slide is there? Compacted graphite iron. Skeleton over here. Yeah. Oh, okay, yeah. Very similar to ductile iron. Here, ductile iron. Okay. It is a type of cast iron as well, which it is not in this syllabus, so I didn't cover that. So don't worry about compacted graphite iron. But it is very similar to ductile iron. Like, from my knowledge, it is very similar to ductile iron, but it is not being covered here. So don't worry about that. Okay. So how long and how many questions again for midterm? Worried about time. Okay. There will be 2 questions, 2 hours. 2 questions, 2 hours, 1 hour for each question. And then I'll give you about 30 minutes for you to submit your all the necessary documents. Essay or structure forms. 2 questions will be divided into part 1, A, B, C, and D, so on. And of course, if it is a structure question, which is an essential and essay question, you need to type it off using Microsoft Word. And all the calculations, you don't need to type it off on the Microsoft. What you take a piece of paper, do the calculation, yes, take a photocopy, and then attach the photo on the Word document. That's all. You need to attach the photo on the Word document. Let me see. Okay, I'll teach you how to do the easiest way for you to attach a photo. Let me open a photo. Hold on, guys. Hold on. Okay, guys. This is just a tips, okay. This is just a tip. I'm very sure that you are much more better than me on Word documents, but this is how I do. Okay, this is how I do. Okay, this is your Word document, right? So you are writing an answer 1, blah 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 blah. Okay, you can view the Microsoft Words, right? Can you view the Microsoft Word, guys? Okay, so whenever you want to attach photo, the best thing is you go to, this is how I do. I feel easier. I go to insert. And I click on table. I just, let's say one photo. Just click this. And then over here, what I'll do is I just drag the photo, any photos that you have taken, and drop it here. That's all. And then resize it. This is the easiest way that I've learned. And click on, no, I don't touch this, okay? Then what you'll do is you click this, and this figure is referring to question 1. That's all. Then what I'll do is I click this, and on the design border, I'll remove the border. That's all. Finish. Then you have question 2. Answer blah 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 blah. Then you want to add a figure in question 2, insert table, 2 things, because the reason why I insert table is it will perfectly align the image. When I want to add another image, just click on the another image. Let's go here and paste it here. See, it's perfectly aligned on the table. Resize it and make it center. This figure assigned to question 2. Make it center. Then you're done. Click here and you just remove the borders. That's all. Okay. This is question 2. This is how I'll do lah. I'll just create insert a table. So question 1 is about Batman. This is the image that I have in my desktop. So I mean, you got it right. You got it right. So it's easier. Instead of, when you drag and drop an image, let's say the same image I'm dragging in Word document. So it is loading and it is huge. See, sometimes it is so huge that it might overlaps the whole screen, and the Word document might hang because the size is bigger. So when I create a table, the Word document will automatically fit the picture in the table. I don't know about these guys. I mean, I don't know you know or not, but this is how I do. I might sound outdated, but you might have a better solution for it. I don't know. Okay. Oh, so the picture you are referred to the picture of our answer. Yes. No. Yes, the answer. Let's say the answer requires calculation. You do the calculation in a piece of paper. You take a photo from your phone and transfer it to the computer. And then from that, the image you can just drag and drop in the Microsoft Word. Okay. This is what my lecturer taught me when I was doing my PhD. Okay, I don't know, you might have some better ideas, So whenever I want to delete this, you can't, it's very difficult for me to delete this. I can't delete, you see, I can't delete. When I press delete, it doesn't delete. So what I'll do is I click this and I just Control X, cut. That's all. When I want to delete this, I click the whole image, Control X. That's all. I click here, click the whole what they call figure, Control X. Delete. That's the delete for me. Okay. You know why students will tend to panic when there's a time restriction. So I don't want you to panic. So these are the tips that I can give you lah. My hands shaking when I take. Make sure that it is well lit. Most time consuming part is transferring to PC to yeah, transferring the picture to PC. Do you have Dropbox? Guys, do you have Dropbox? Dropbox. Okay, maybe you can download Dropbox. Dropbox is a file sharing, something like file cloud sharing. No, cloud space for your own personal usage. So what do you do? Download Dropbox in your computer and also download Dropbox in your phone. So whenever you have taken a photo, you take the photo and drop the photo into the Dropbox of your phone. So it will automatically sync to your computer where the account is being associated with. No, Dropbox will never reduce the image size. Dropbox will transfer as it is. So it is not necessary for you to plug in using wire and then no. Try to get Dropbox